like 25% alpha. Oh, you can't even tell on this. That's so dumb. I know because sometimes you're like, I'm sure this is the answer, and you get this answer. It's like, this is the previous attempt. I got it wrong.
Okay, so I crunched all the numbers and got the results of exam 1. So I've made a posting on announcements here. You can see your score out of 100, and this was the range. This is the distribution of scores. Once I got your final score for you, our average was 70, median 73. So if it didn't go as well as you hoped, you know, you're not disqualified from anything in one test. It's just that you have less of a cushion. You have to improve at the right amounts to get what you were hoping for. So just take this first exam as a learning. You're learning how the course is going. You're learning what I'm expecting of you, so you can prepare. You can be more ready to how to prepare for the next exam. Okay, which is you got to understand stuff, right? So I'm going to ask questions to see if you get it. All right, as well as can you do the problems? Okay. So that's there. You can see your score. We looked at this last time. Let's do another example with this. So I had this function. Vector functions, right? What's the independent thing in a vector function? Scalar, right? A scalar. So it's a set of values, scalars. And each one of those scalars gives us a vector, right? So by saying vector function, we're saying that the result is you're getting vectors. This function is spitting out vectors at you, right? And so this, if we want to be more specific, this is a single variable vector function. Single variable is referring to what you put into it. One single scalar, and then from that scalar, you get a vector. Each of the components of the vector is a function of the scalar that you put in. So this one is t 2 sine t negative cosine t. And so I've kind of stopped life here on this particular point, which is t equals pi. All right, so t equals 3.14. And so I want you to review. So we got 4 different vectors. I've changed up the colors on you, if you can see them. So there's red, purple, blue, and black. So I want you to do several things here. We're going to identify the vectors by their color. So what is the vector representing? For instance, it's the binormal vector, or it's the vector of the function itself. Okay, and then want you to find all the vectors. All right, so we're going to actually find them, and then we're going to eventually find all the planes that go along with these vectors, right? So we said with the tangent, normal, and binormal vectors, they're all unit vectors. They're like a little coordinate system that follow the curve, right? So and then each of those, along with the coordinate system, you get the planes, right? You have that little coordinate system has 3 planes: the tangent plane, the normal plane, and the osculating plane. So we're going to find all that stuff for this example. Not going to take a long time, but we are going to do all that. So I'll do roll. You can talk, and I'll just keep showing you different views of this. So what are the vectors? Like, what are they representing? Meaning, how do we call them? So and then find the vectors. So talking numbers now. Any way you can. Okay, so just any way you can. He wants the red one. Agree? Okay? And so then which one's the unit tangent? Curry. The unit tangent? Curry. You don't know. Okay. So talk. So that discussion is, you should figure all this stuff out while you're talking. Okay, so how about Jackson? Purple. He wants purple for the unit tangent. Pointing in the direction of the curve, right? Agree? Purple? Okay. Unit normal, Alyssa.
The black one. One on the top. Yeah. The black. Not the one pointing. The black one's pointing out.
This one's the unit normal. Agree? Shane, you agree with that? So remember that the unit normal points in the direction of turning. So when we're at the top, which way are we turning? Which way? So if you're driving a car along this, which way are you, when you're at the top, which way are you turning? It's kind of hard in 3D, so the car kind of breaks down in 3D. But which way is it turning when you're at the top? Which way are you turning? Down, right? You see this, the other one? So when you're at the top, you're actually turning down. So the blue one is the unit normal, and then the black one is the binormal. Okay, so let's find the actual, how do we find the red vector? The actual vector at this point, what would we do? So just put in pi in the original function, right? So this is for our value of t is pi, and so we would put pi, and so we would get pi, and sine of pi is 0. So we're doing, what are we doing? We're doing r of pi. So we're going to get pi, 0, and positive 1. Does that vector look like pi, 0, 1? Just from as a quick check, as a view. Coming out 3 in the x direction, 0 in the y direction, up 1. Looks about right. See that? Out about 3, a little more than 3, up 1, and then, or no y component, and then up 1. So we're good? Okay, so any of the others that we can just find right off the bat? We just know. We can just say, this is what it is. Yeah, John. Where's that?
Blue one,
yeah. Straight down. And what's its magnitude?
-1.
Yeah, the magnitude's 1, and it's going straight down. So what vector would that be? So this is, and what vector was that again?
It's the unit normal.
Normal. So it's going to be the unit normal at pi. And we can just write it down. It is? He wants 0, 0, -1. Agree? Yeah, because it's pointing straight down. Because we're at the top, pointing straight down. We know the magnitude is 1, so straight down is in a negative z direction. Okay, next. So the easiest one to find, so these others, we don't really know for sure. There's not really symmetry there. If we look down on this, we might see some symmetry, but we don't have symmetry, so we gotta do the math. Which one can we find easily or first? Unit tangent or binormal? Unit tangent, right? That's kind of the easiest one. So what is the unit tangent? Yeah, so we're gonna do the vector derivative function, and then unitize it or make it have a length of 1. So our prime is 1, 2 cosine, and positive sine. So we can do two things. We could find the unit tangent function and then plug in pi, or we just find this vector at pi and then unitize that. Okay. So the first one gives us more versatility because then we would know the unit tangent at any t. But for our purposes, we just want to know this particular unit tangent. So it's easier to actually find r prime of pi and then just take the unit vector for that. So this is easier. R prime of pi is 1, -2, 0, and then? Yeah, so that's square root of 5. So it's going to be 1 over radical 5, -2 over radical 5, 0. And let's check that out. Let's make sure that looks right. So I'm going to look down on this. So we know the z component is 0. Looking down on the, what? The purple. So x coordinate of this vector, positive, y coordinate negative and twice as much, right? So positive 1 over radical 5, negative and twice as much, looks right. Make sense? Okay, let me just give you some, if you were just finding these functions, say we found the unit tangent function, and then you're going to take the derivative of that and normalize that to get the unit normal, that is often really terrible algebra, just because you first find the derivative, then you're going to find, you're going to have 1 over square root of the magnitude of this for each one, and then you're going to take the derivative of that, right? And then take the magnitude of it to get n. That's awful. It's usually, if the function isn't very well rigged, doing this can be really, really long and terrible. So I think there's one time when I ask you to do it. Maybe in the web work you have to do it one time, and maybe written one time. But whatever you can do to avoid this. Like, for instance, what I did here, right? Just if you know you want it at a particular value of t, little t, then get those vectors and then work it through. Rather than, now you can't take, if you do that, you can't take derivative, right? So once you take a derivative of that, you get 0. So you have to hold on to your functions as long as you need to. But if there's ever a choice where you can plug in a little t to help you do this, do it, right? Because this is just can get awful. And then you got to cross product that if you want b. But I'm going to show you a different way to get b. We know what do we know about the binomial vector here? Okay, it's the cross product of t and n. But just from this example, what can we say right off the bat about? We know that the unit normal is 0, 0, -1, which means what about the binormal? Its z is 0 too, right? Do you see that if the normal is 0, 0, -1, then the osculating plane, which is the plane that the tangent plane will contain both. The tangent plane right here is going to be a horizontal plane. It's going to contain both t and b, right? And it's written by n. Okay, so this one's going to have right off the bat. We know that has a z component of 0 because it's in the tangent plane. Are we good? Now I want to show you a trick. So now, what's true about the relationship between t and b? What do we know about t and b? Or given any two of the vectors, what's true about any two of the vectors? They're orthogonal. See that? So now I'm looking down on it, and we know that what? T is 1, it's in the ratio of 1 this way and -2 this way. In order for b to be orthogonal, do you see that you can kind of use the symmetry of this? So its components, so we had what? We had 1 and -2 as a ratio. So what will the ratio of x to y be for this, for b? X to y. So x here for the unit tangent was 1 and then to 2. So what about now? X is how compared to Y? Yeah, do you see that it flips? When you have orthogonal vectors, it's like your X and Y coordinate. If you're in an R2 situation, like your X and Y flip. But then we got to get the signs right too. So what's the sign in X? Positive. So it's going to be what? Positive 2 over root 5. And then what about Y? Positive or negative? Positive. Magnitude? So do you see what happened? Rather than calculate the cross product, I've got a situation where I know Z is 0, and I know it's orthogonal to T. So I just see the relationship here. This is 1 and then negative 2. So then X would be 2 and positive 1 to get B. So I can just switch them and get the signs right without having to do the math. So this is a helpful technique for these. And then we can check that the dot product should be 0, right? 1 over radical 5 times 2 radical 5 plus negative 2 radical 5 times 1 should be 0. And it is. Okay, so the general principle here is that, if you have a vector like this, and say the vector is AB, then what would that vector be? And they're orthogonal. So my original vector is AB. What would this orthogonal vector be in the second quadrant? What would the x-coordinate be? Negative, not A, right? So do you see? See, this is A here, and this is B here. So now this would be what? That'd be B, and this one would be A. So the components would be negative B, comma A. So the magnitudes flip, and then you just got to get the signs right. It's just a helpful trick for finding orthogonal vectors in R2, in an R2 situation, like we had here with T and B. Yeah.
And we just did that because they're in the same plane.
Yes. Well, they're in a plane. They're in a coordinate plane, right? So they're parallel, so we know that Z is 0. But as soon as this thing is tilted a little bit through space, then we can't do that.
So this is just like a specific instance.
It's the instance where it's an R2 situation. It's like this. And we had that because the Z is 0 for both of these. Okay. So, and then we could write to write the tangent plane. We'd use our point pi 0, 1, and which vector to write the tangent plane. Which vector would we use to write it? So the tangent plane would be a horizontal plane, right? The tangent plane. You use the normal vector to write the equation of the tangent plane. We want to write the normal plane. That would be something like this. Normal plane would be like this. Which vector? The tangent vector is the one orthogonal to the normal plane. And then the osculating plane, it's the plane it's this one. It's like the plane that the curve is in at that moment, right? So it's coming around like this. So it's right at that moment, it's like in this plane here. And so its vector is the binormal. To write its equation, you use the orthogonal vector to the plane, which is the binormal vector. Okay, so we've used up a lot of time on this. Any questions on that? Okay, so let's talk about curvature. Okay, so curvature is a number that tells us like how curved the curve is, right? It's a number that puts a number on how curved the curve is. So what would that be? So that we use kappa. So that's a function, right? So as you move along the curve, the curvature can change, right? So it's a function of that scalar wherever you're at on the curve. And so here's the general idea. So it's how much the unit tangent changes, and that's purely direction, right? The unit tangent is a unit vector, so that the change in the unit tangent is really just talking about the change in direction. How much does your direction change per arc length, right? Which makes sense. Because if it changes a lot for a little change in arc length, then your curvature will be high. Should make sense, right? If your direction changes a lot for a small change in arc length, that means you're twisting fast, right? And if it doesn't change very much for a long change in arc length, then you're almost straight, right? So then you get a low number. So this is another way to think of it. It's the derivative of the tangent, which is again change in direction, right? Change in direction of the curve per what? Change in arc swept out, right? Which is r prime. R prime is the derivative function is how much of the arc do you get for a change in t. Okay, so this is the idea, but you never calculate it this way. Okay, you never use this to calculate it because we know that this t prime is bad enough. Okay, so here's what we'll use. This is a formula you use in R3. Okay, so in R3, it's the cross product of the first derivative of a vector function and the vector second derivative function, the cross product, and you get the magnitude of that, and then you divide by the magnitude of the first derivative cubed. And I didn't derive this. I didn't show you where this came from. So I just told you, okay? So in R2, if you have y as a function of x, it's this formula. So you take the second derivative, take the magnitude of it, divide by the magnitude of the absolute value, so absolute value, 1 plus the first derivative squared, absolute value, raised to the 3/2 power. Again, I didn't derive this, I'm just telling you what it is. And then in your homework, there's still another formula that they give you, and you use that one. So there's different formulas. So use whatever one makes sense in the moment. Okay. So we'll use this for R3 when you have a vector function for your curve. This used in R2 when you have just a regular scalar function as your curve. Okay. So if a circle has radius a, what is the curvature? All right, so we're going to do that. So I want to find the curvature of a circle with radius a. So how can we write, let's use this first formula. So I need to write the circle as a vector function. So what's the simplest way that I can write a circle with radius a as a vector function? Yeah. What is it? It's got to have a radius of a, though. What is it? What's that? Not square root of a. A cosine, right? A sine. And then 0. So we'll just put it in the xy plane. Okay, we'll just put a circle in the xy plane with radius a. And then we got to do the math, right? So we're going to do the math to figure out what the curvature will be. So I'll just do this fast. So what do I need? I need the first and second derivatives, first of all. First derivative is negative a, and I'm just going to go with st and ct. Just as long as you know what you're talking about in the context, it's fine. And my second derivative is negative a cosine t, negative a sine t. And I'm going to take the cross products. ijk, negative a sine t, a cosine t, 0. negative a cosine t, negative a sine t, 0. Cross product. So the I and j, because of this 0, 0, the I and j components will be 0. And the only thing I'll get is a k component when I do the cross product. So the k component will be, looks like positive a squared sine squared. And then minus negative a squared cosine squared, or plus a squared cosine squared. So I'm just doing the cross product algorithm there. And what is that? What vector is that? 0, 0, a squared, right? Because you factor out an a squared, and you get sine squared plus cosine squared is 1. And so that's the numerator is the magnitude of that. So the magnitude is 0, 0, a squared, a squared. Okay, that's the numerator. I took the cross product of the first and second derivatives, and then took the magnitude, a squared. So then this, we need the magnitude of the first derivative. What's the magnitude of that? Give me the square root of a squared sine squared plus a squared cosine squared. Which is a. And then I'm going to cube it. Right? So this is going to end up being a squared, my numerator, over a cubed equals 1 over a. Follow all that? Where did I lose you? I went fast. Yeah.
I just have a question. For the one in R2, you take the magnitude and then still 3 over 2 root it?
Well, it's the absolute value here.
Okay,
Yeah, you can take the absolute value of this quantity and then take it to the 3/2 power. But this is different because you don't have any vectors in this. This is just all with the scalar function. So we're doing it using the vector function. So it's different. But yeah, you take the absolute value of that and take it to 3/2 power. All right, questions on this derivation? So what does it tell us? Does it make sense that the curvature of a circle with radius a is 1 over a? Why does that make sense? The smaller the circle, how's the curvature of a small circle? High or low? Super high curvature, right? You're like for a little distance, you're making huge turn. So for a small circle, this number's going to be big. And then for a really big circle, got a huge radius, curvature high or low? Very low. It's almost going straight, right? So for a huge circle, you're going to get low. It should make perfect sense, right? But it's the simplest function that has that inverse relationship, which is nice, right? So there's all kinds of functions you could have where it's this inverse, one is big, the other is small, but it's the very most simplest one you have, right? It's 1 over the radius gives you the curvature of it. Curvature of the circle, 1 over the radius. Okay, so that leads us to something called the osculating circle. The osculating circle. So any questions on this derivation? All right, so this is kind of cool. So here's a function. And so the osculating circle, it's like a circle that's tangent to the curve with the same curvature at that point at the curve. So at the So let's just talk about curvature. Where's the curvature the highest on this function, 1/6 x cubed minus x squared? Where's the curvature the highest? At the local max and min, right? You see that? And then where's the curvature the lowest? away from there, right? The further you get away from these local, and actually there's a place of zero curvature right in between, right? The inflection point is like, an inflection point is like you're heading straight, you're not curved for that moment. And so that's zero curvature. So now the osculating circle is if you take the whatever curvature you're at and make a circle that's tangent at that point, so it has the same curvature and is tangent at that point, that's called an osculating circle. So where do we expect to see the smallest osculating circles? Where the curvature is the highest, right? And we said that was at the local max and local min. And then away from there, where it straightens out, we're going to see what's this oscillating circle going to be like. Bigger, right? So let's start, say, here. So there's the oscillating circle for that point right there. And so if I move away, so the minimum radius is maximum curvature right here. Minimum radius, maximum curvature. And then as I move away, what happens? It gets big, and then it gets really big because what's going to happen? Now it's still a circle. I'm not quite at the inflection point yet. Watch. So that's the osculating circle. Its radius is in the hundreds, right? Like 600 or something, 700. It's so big because the curve is almost straight there. And then it gets super small again where the curvature is high. High curvature, low radius. And then you just talking about out away for large x and large negative x, you're going to be a huge oscillating circle because the curvature is so low, almost straight. And it's going to flip over. Okay, so it's tangent to the curve with the same radius. Tangent to the curve with the same radius, or same curvature, is what's called the osculating circle. And so then if you'd have this in R3, then in R3, you know, this oscillating circle could be like, you know, all over the place, right? It's easier to imagine in R2. It's all over the place, but it's the osculating circle. So what plane is it in? It's always in the osculating plane, right? That circle is going to be in the plane that the curve is in at that moment. And that's the osculating plane. Okay? So let's do a little practice problem here. Let's make an easier function, first of all. We'll just do x squared. And we'll do it at x equals 1. Okay, and our goal is, we want to find the equation of the osculating circle using what we know. We want to find the equation of the oscillating circle. So what do we need to write the equation of a circle? Center and the radius. Okay, so we've got all the tools. We just got to put it all together. So the equation of this circle, we need center and radius. Do we know any of those right off the bat? Do we know the center? Certainly not. We're going to have to figure it out. What about the radius? Okay, well, let's do the radius first. How are we going to get the radius? Right, so we're going to get the curvature of the function at this point, and then do what to it? 1 over. So the radius is going to be 1 over the curvature at, that's supposed to be a kappa, on an x. At x equals 1. So the radius would be the curvature. Let's do that first. So we've got y equals a function of x in R2. This is a perfect chance for the formula I gave you for that. So x squared. So let's find it as a function. So the curvature x equals what was it? Second derivative. Absolute value of the second derivative. First derivative is 2x. Second derivative, 2. Is that the whole numerator then? Are we done? Absolute value of the second derivative. Okay, so it's 2. First derivative is 2x. Second derivative is 2. Over the absolute value of? First derivative is? 2x. Square that. And that whole thing raised to the 3/2. Okay, so that is the absolute, that's the curvature function, right? That would give you the curvature at any value of x along the parabola. And we want it at 1. We want the particular curvature at 1. Oh my. So it's going to be 2 over 1 plus 4 is 5. 5 to the 3/2. Did I do the math right?
Yeah.
And so what is that? That's 2 over the square root of or 2 over, that's 5 times 5 times 5. 5 radical 5? Good so far? So radius is? So the radius we want is 5 radical 5 over 2. Have we done all the math right so far? Please, if you think there's a mistake, please speak up. Okay, and now how are we going to find the center? So we have the tools to do it, but I want to leave you guys to think about that and figure it out. How are we going to find the center of this? Right? It's somewhere over here, right? It's somewhere over here. We got to figure out exactly where it is. John has an idea.
You would take the normal vector,
The normal vector.
unit normal vector, and then multiply it by the radius.
He wants to take the normal vector and multiply it by the radius. So why the normal vector? It's orthogonal to the curve. Is the normal vector going to point at the center of our circle? Yeah, you said that should feel right, right? That the normal vector at that curve right there, and it's going to point right in the line of the center, right at the center. So then we're going to take the normal vector. What's the magnitude of it? It's 1. And how far do we need to go? R. So if we just scaled up the normal vector by R, and then did what? Vectors are mobile, right? So put its tail at our point, and then scale it. It's going to take us right to the center. Okay, so what is the normal vector at 1? So here we can use our trick. Okay, we can use our trick. We don't have to do. How can we figure out the normal vector at 1? Start with. How are we going to get the normal vector now? Okay. Find the tangent. All right. How are we going to get the tangent? First derivative. So first derivative, f is 2x. And we're at 1. First derivative 1 is 2. Okay, but that's not the tangent vector. What is that? That's the derivative. That's a number, 2. So to get n, don't we need t? So how does the number 2 relate to this vector, this unit tangent vector at 1? What's that? Yeah, so it's like rate of change or slope, right? So what does it mean? It means, so what does it mean about the relationship of those components? The fact that it's the rate of change is 2, or the slope is 2. Right? For every 1 unit, x increases, or for any change in x, y changes twice as much as your change in x. But then we also need this to be what kind of vector? Unit vector. So we need the unit vector that has a y component that's twice as much as the x component, right? Do you see that? The 2 told us that the ratio of y to x was 2. We also need it to be a unit vector. So how do we resolve those two things? We could say you could just say c and 2c, and then we need to make sure that's a unit vector. Or we could just start out with 1, 2 and unitize it. So it's going to be in the same direction as that, but then we need to make it a unit vector. So it'll be 1 over radical 5 and okay, and then here's our chance. We can use our trick, right? We got the unit tangent vector, 1 radical over radical 5, 2 over radical 5. What is, everyone see if you can do it. So if this vector is 1 over radical 5 and 2 over radical 5, then what is n? If you understand the trick, you can just write it down. X component is? Good, negative 2 over radical 5. And y component? Positive 1 over radical 5. We know it's negative x, but now its x component is the y component over here, right? Because it's going mostly up here. This one goes mostly over. And then up 1. All right, so we got to put it all together. We got the what point is this? This is the point 1, 1. We got the normal vector, negative 2 over radical 5, 1 over radical 5. We got the radius, 5 radical 5 over 2, so we just got to get the center out of all that. So I'll call that the c vector for the center. Equals what? Can we make an equation that will get us this center vector? Not x, y, but just c. So how can I put this all together so that C is the center? Jorge.
You're going to do r times the normal vector that
Okay.
we first got. So it's going to be 5 rad 5 over 2.
Right?
And then brackets negative 2 over r.
You're right. You're right.
Negative 2 over 5 rad 5.
Okay, and
1 over rad 5.
good. And that give me the center?
You need to add what you started at, so 1.
And then add the vector what?
Add where the point you started at.
Right.
Trying to figure out, so
Plus 1, 1. And that'll be the result will be a vector whose, if in standard position, will give us the right coordinates. So we scale the normal vector by the amount of the radius and add it to my starting point, 1, 1. And that'll take me to the center. Should make sense. Everyone follow it? So what do we got? Radical 5s go away. Negative 5. Is that right? Negative 5 and plus I'm a little nervous because I remember this problem right. We got weird numbers for the center, and this isn't weird. 4 7/2. Negative 4, sorry. Negative 4 7/2. Does it look about right? Okay, good. So now I'm gonna graph another circle in my software here, GC, based on the radius and center that we found, and what should happen? We should only see one circle still. I should graph it right on top of it. Everyone got this written down? Can I erase everything? Here we go. So we want our circle to be, equation of the circle. What's our x-coordinate? Negative 4. So x plus 4 squared, what? Plus y minus 7/2 equals 5 radical 5 over 2. I'll just do that. 5 radical 5. Oh, I'm just going by my memory. Is that right?
Make sure you split it.
Square.
Then you square it. Is that right now?
And the Y.
Oh, thank you. Thank you. Now do we have it? So I think it was blue before, right? Blue plus red makes indigo. Here we go. No.
Your slider's at 1.
Ah. So we'll just say n equals 1. N equals 1. Nailed it, right? So turn it off, turn off the red, you only see blue. Turn it on. There, got it.